This is the comparison again. So you will be short of D and E. Then I would roughly kind of just skim through, talk about it. So you have this. You must know how to describe the production of sound. We need to know sound wave is a form of energy. Sound is a form of energy, and then we need to know it's a longitudinal wave. So because it's a longitudinal wave, you will expect the vibrations to go this way and the wave motion is this way, same. So they are parallel to each other. You expect that. Then you need to know that sound is produced by vibrating sources that is placed in a medium. So it could be, let's say, the tuning fork, and the tuning fork is placed in a medium probably air. So when you put tuning fork in air, you will create a sound. Then in order for you to hear the sound produced by this tuning fork or any vibrating sources, the vibration must be transmitted to your ear. If tuning fork is not, you're not familiar with it, you can also have another situation where you have the plastic ruler. Then you put it at the edge of the table, and then you just flick it. When you flick it, you get a vibration as well. Then you will actually hear you hear the humming sound that is made by the plastic ruler. That is another. I mean, if you want a more an example that you can more closely relate to. So how you get that sound from the ruler is because the ruler is vibrating. And then that vibration from the ruler, that energy is transmitted to our ears. So that's why we hear the ruler humming away. Okay? Okay?
Yeah.
Yeah. So then you have this some extra information. So in that animation, that is a supernova. So a supernova is the explosion of a star. Then the star I'm talking about is the star that we have in outer space, not on Earth. It's out there.
Stop.
So then it's out there. So then my question is, can you hear a supernova? Because you
No,
say it's an explosion. Boom. So you have this massive explosion of the star right out there. Bam. Can you hear it?
no,
Hmm.
because sound cannot travel in a vacuum.
Yes, that's the whole point of this example. Say you have to say that sound cannot be transmitted in the vacuum because there's no particles. Because there's no particles mean no medium. Because of that, you cannot hear a supernova. Okay? Hmm. So this is a star here. So now back to our tuning fork. So we have a tuning fork down here, and then I hit the tuning fork on the table, then I leave it. Initially, the air layers in front of the tuning fork is undisturbed, right? So then the tuning fork starts to vibrate. So it will vibrate this way, and then after that it will go back this way. Then the tuning fork going out and inwards and outwards again and inwards again. This thing repeats itself. Okay, so you have a vibrating object. So this vibrating object is a tuning fork. So it will produce sound waves through shifting layers of air particles in front of it. So we come back to the drawing, and then we see this is the first layer, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. What can you say about the position of the layers of air on the second diagram?
And refraction.
So you see, you compare the position, you see the first layer was here, then the first layer now is here. So the first layer moved to the right, right? Then this remains the same. This remains the same. Number 4, again, it shifts to the right. Then number 5, you see here is here. So that means it shifts to the right. 6 remains the same. Then 7 remains the same. Then 8 shifts to the right. Then 9 shifts to the right. 10 remains the same. 11 kind of the same. Maybe not the same, a bit off. Then 12 is this way. 13, is it this way? Then this one like that. So you get from here to here, you see layers of air shifting. So when layers of air shifting, you get this. So after some time, you will get a series of compression and rarefactions via this shifting of layers. That's how you get compressions are the layers, air layers, right, coming very close together. Rarefactions are areas where you'll see your air layers are further away from each other compared to normal.
Compressions are regions where air pressure is slightly higher than other regions.
Yes, when you have a lot of air layers come together, squash together, then your air pressure is high. So when you have many layers of air and they are further away from each other, that means the air pressure is lower there. Then if air layers, right, are even out like this, right, then it's the air pressure is uniform. Here is air pressure low, and here is low, high pressure. So how you see air pressure high, air pressure low is how the layers of air, if the layers of air are equally spaced out, that means the air pressure is uniform. If the layers, right, are very close to each other, that means it's a compression. If that means the air pressure is high. If the air layers are far away from each other, that means it's a low pressure region, then it's a rarefaction. So this is how you see it. Okay? Okay. I'm moving.